Hello, my name is Joshua Frieze. I am a student at Grantham University College of Engineering and Computer Science. Today I would like to discuss with you a capstone project executed by myself and Mr. Timothy Ganger. The project consists of a remote climate simulator or an artificial sun. The instructor for this course is Mo. Just Mo. And let's get started. Through the course of this presentation, we will cover a few different topics. The first topic we'll discuss is the course scope for the EE450 Capstone project class. Secondly, we'll go over a design overview of the project, moving on to the project model, a block diagram, a software flowchart, and a parts list, followed by an interface and output stage schematic, and then finally, a short presentation video which will show the function and operation of our simulated sun. The overall objective of this capstone course is to execute the project as initiated and planned in the EE410 project management course. For this project, we are executing Tim's idea for a remote climate simulator. The overall scope of Tim's remote climate includes things such as wind, rain, and other environmental factors. The simulator is connected to a remote weather site, which provides the data necessary to simulate the distant environment. However, for the purposes of this course, we have simplified the project and will implement only the artificial sun simulator. The final product for this project consists of an Arduino controller interfaced with an 8-channel interface module consisting of a zero cross-reference and 8 individual output channels. Input isolation is achieved through the use of opto-isolating triac drivers, and zero cross-reference is also achieved using an opto-isolator. The physical design for the finished product, minus the interface module and the microcontroller, can be seen in the following images. As you can see, the final product is an arch consisting of 8 individual light bulbs, which will be operated by the 8 individual channels on the interface module. One end of the arch is considered pseudo-east, the other end pseudo-west. Diagram shows how the Arduino microcontroller receives data from a distant weather site. This data is converted into 8 channels of pulse width modulation, or PWM, which is then transferred to the interface module, which uses these pulse width modulation signals to control opto-isolated triac drivers. The triac drivers are connected to triacs, which act as a dampening gate for the 120 volt power supplies for each of 8 incandescent lamps. The lamps are controlled in such a way that simulates the sun cycle for one given day, based on factors such as cloudiness, temperature, and time of year found in the data received from the remote weather site. During the design phase, Tim had budgeted $500 in order to purchase and procure all components required for this project. However, you can see in this parts list that our total cost for all components, including lumber, electronic components, the Arduino microcontroller, wire, and all other miscellaneous components, came in at a grand total of $175, $325 under budget. Here you can see the interface and output stage schematic. On the left is the terminal block, which is connected to the Arduino microcontroller, consisting of the 8 inputs for the pulse width modulation signals and the pins which will feed the Arduino with a zero cross reference. A second terminal block connects the interface with the output stage, which consists of 8 incandescent lamps. As you can see by looking at the schematic, the goal of the interface module is to take a PWM signal from an Arduino controller, run it through a optocoupler that drives a triac that acts as a dampening gate for the 120 volt supply voltage for each of 8 channels of output to 40 watt incandescent light bulbs. And now I'll turn it over to Tim as he presents the hardware and functional tests of the artificial sun simulator.
My lab partner built this board. This is for the pulse width modulated feature that will be incorporated. This is the zero crossing detector circuit. The lower scope trace is the 120 volt AC. The upper trace is the 0 to 5 volt output of the zero crossing detector circuit. Here you can see the pulse width modulation on the scope top line and the shaped AC waveform on the lower line. Over here is the actual sun arc. As you can see, the bulbs are turning on from pseudo-east through pseudo-west. Pardon my messy lab environment. Up until a week ago, this was a nice, tidy academic office, and now it is turned into a full-fledged workshop. Notice each light bulb overlaps its time slightly. This would be the 12 o'clock sun, where it has a longer dwell overlap time to simulate a peak of day.
And as you'll notice, the lights are not damping, they are merely turning on and off. Tim and I agree that this is a hardware issue. However, due to time constraints, we are unable to troubleshoot at this time. We will, however, after the completion of the class, look into it and correct the issue.
And the sun is setting in the pseudo-west.